And the first talk, I will be the chairman for just for the first talk. And since our first speaker is not so well known in the gravity community, let me say a few words about him. So Philip Walther is professor at our university, and among other things, he's head of a research platform called TOURIS, which you can see on the screen. It is testing the quantum and the gravity interface. This is a platform of several research groups, including experimental and theoretical know-how in quantum physics, such as entanglement of photons, matter waves entanglement, and also nanomechanics devices. And from the other side, the gravity physics group here in Vienna. Philip is an expert with entanglement of photons, and therefore his talk, his title of his talk is Shining Light on the Interface of Gravity and Quantum Physics, Position Measurements Using Photonic Quantum Interferometry. Please, Philip, the floor is yours.
Thank you very much for this nice introduction. Before I start questions, do you hear me? Can you hear me well?
Yes, I can hear you.
Okay, perfect. So it's a pleasure to be here. I feel like a little bit a party crasher because I'm the experimentalist and have the chance to talk to so many theoreticians, which is always inspiring as they guide us in the design and basically in the steps and experiments. As you already heard, I'm a quantum photon guy, so my background is photonics, and we have now for a couple of years a particular interest in using our quantum photonic technology to really investigate the interface of gravity and quantum physics. And within the next hour, I hope I can entertain you by showing you how we plan to do that and what's the current state of our research. A couple of years ago, we founded this research platform TOURIS, which is our vehicle where we perform the experiments and basically have this collaboration among different groups to really tackle this interesting problem. So I would like to move on the slides, but it doesn't allow me to do so. Why is my computer is frozen? It's like let me see whether it doesn't work. No, here we go. Okay. Well, as you know, our universe is based on a few beautiful theoretical pillars. We have general relativity that allows us to explain or to understand more or less the macroscopic cosmological sizes. We have this field equation of Einstein who basically map gravity with space-time on the very small scale. We have at the moment a standard model where we can put the electromagnetic forces together with weak force and strong force, which also beautifully explains the interaction there. We also have other theories where basically there's an interplay, and we would like to understand the interplay. So we have, in a nutshell, I found this nice schematic drawing where people separate between classical theories, classical mechanics, electromagnetism, and quantum theories. And the black arrows here show where try to find my pointer again. Sorry, here's the pointer. The black arrows should show basically the influence of one theory led to the development of the next theory. So classical mechanics led naturally to Newton gravity, and then later on it led to general relativity and so on. It's basically as a follow-up into the theory development. And as you quantum mechanics was basically further developed to quantum field theory and so on. But the open question is, as you know, where basically do we see a combination of those theories? And these are the dotted lines that show it's unclear yet how those things basically fit together. For example, is there a quantum theory of gravity that involves all those concepts and so on? And what's the natural way to investigate these questions besides doing beautiful theory is, of course, to do experiments that give a guidance on those developments and how they interplay. And that's basically the motivation of TOURIS. We're all scientists, okay? And at the end, I think if you ask us what is the passion that drives us, or what's mankind's desire, then I think it's beautifully phrased by this German poet and poetry writer, Wolfgang von Goethe, who has this famous phrase from Dr. Faust. I think he was unhappy because we like to understand nature. He says that I recognize what holds the world together inside. Okay, or in German, dass ich erkenne, was die Welt im Innersten zusammenhält. And I think that's the motivation for us as scientists to really investigate these kind of big questions. And if you map this to what we can do with our skills, or at least with our background in Vienna, it turns into the question from tourists, which is, how does gravity act on quantum systems? Okay, and to be more precise, because tourists was initially considering only photons, now we extended it to also consider other systems. But going back to photons, which is my background, the question turns into, how does gravity act on massless quantum systems? And I will mention this a few times why I focus on massless, okay? And of course, including quantum entanglement, that you see how those things interact and what we can learn there. And if there's something maybe unexpected happening, we don't know, okay? And that's the thing. Our duty as experimentalists to really take a step along this line. Good. So general relativity is basically the vehicle we would like to see and basically face it quantum mechanics and interplay. And for that, I would like to take a look back about the experiments that really were the first to see and observe general relativistic effects, and that also can put our experiment that we have right now in mind to do in the right perspective with respect to the previous experiment. So I guess you all probably know, it feels like it's bringing cold to a castle, but never mind. I like to rephrase this and show you again. If you think you all know this, it's an old story, then I'm happy to cut this short and accelerate to the next slide. But coming back to the review, I would like to basically show you, well, for me, the beginning of the first classical test of general relativity go back to the Mercury-perihelion precession, where Urbain Le Verrier in 1509 observed that there's a deviation, okay, of the rotation of Mercury basically moving around the sun. So it's not a perfect elliptical circle. He has seen there's a deviation of this 38 arc seconds, which is almost nothing, like it's basically a micro radians within a century. Okay. Actually, personally, I'm deeply impressed that he was able to observe this. When I imagine how hard it is nowadays to measure those tiny phases, they were able to do it, and he has seen, okay, there's something which doesn't fit into the Newtonian description, which nowadays we know comes from the effect of space, time, and mass. There were follow-up investigations. Simon Newcomb in '82 did it a little bit more correct, or could basically do it more precise, and he came up to 43 arc seconds deviation within the century within that time. That was the beginning where people observed really this general relativistic effect by measuring it. I think for me, the next big jump was by Arthur Eddington, who was heavily influenced by Einstein's work, and he used the total solar eclipse in 1919 to observe here the bending of light. Okay, and he measured here all these 1.75 arc seconds. Solar eclipse means that the moon basically covers the sun, so we basically can really see the light bending. He has two observatories, or used two places with they place regular optics to see it. One was on the west coast of Africa, the other one in Brazil, and they observed this 1.75 deviation of light arc seconds there, which is effect of two different than what Einstein predicted if you just use the regular equivalence principle, because the effect of two is not considered, square root of two depends how you see it, is missing because of not treating also the space-time itself. It was just the time part there, so to say. And here it shows even that the fathers of the concept sometimes get puzzled, but that was here the beginning of basically working with light measurements on Earth along this line. The follow-up was to do it more precise, okay? And what can you do better? So nowadays, many years later, people use this very long baseline interferometry, which is similar to this deep horizon interferometry, where in essence you now have at different locations optical instruments, or here in this case something can even the gamma rays or other things measure, and they are correlated. So the point now is you have very precise timing information about the light coming here. Normally use atomic clocks, and then you can correlate the signals, and by that you get a better, basically a better resolution about those about light bendings, which is done these days. So the pioneer of that, or one of the guys pushing very much, was Shapiro, and since then people have basically continued these investigations. There's one also, you know, the Atacama Desert is used for observatories in Chile. Actually, by coincidence, I was there many years ago, and it really looks like this. Friends took me to a trip, and then I've seen these things there. It's really impressive when you see these big telescopes there. The dry desert is almost 4,000 meters up there, and which is nowadays still used for getting insights into our cosmological things there. Good. The other thing that people also observe is which is related to that, is the gravitational lensing, where basically you see the light bending similar to what the lens would do due to the curvature of space-time. And nowadays it's super impressive that when you take objects far away, the quasars, which are the brightest objects in the cosmos, that you see you get basically values that are very close what's predicted by general relativity. So 1 is the number you're looking for, and people nowadays get a number that close to 1 in agreement with the prediction of GR. And that's still an ongoing research where these days people continue and do this kind of thing. Good, that was light bending. The other thing that people also observed was the redshift, which is nowadays taught everywhere, which is linked to the equivalence principle. That basically you have an emitter and a receiver, and you see that the light is shifted towards red when being here measured at the receiver station. The first ideas to do that was again pointed out by Eddington, as far as I remember, and then later on measured by other people. And what did they do? They looked at very bright objects in the galaxy. They looked at particular dwarfs or white dwarfs, and they've seen this redshift. And they converted this redshift, which actually is a frequency shift, into also a shift in speed. And the speed here is the Doppler shift, the movement that you need to compensate for that. Okay, that's, you find both numbers, either frequency or this kind of speed shift as compensation. And there you see these different white dwarfs that were measured since the 1925 until these days with Hubble. And you see people measure this interesting or impressive redshift from those dwarfs when the light comes to us due to the redshift. Well, that's everything in the big scale. Of course, at the end, you would like to do something on Earth and ground and more or less tabletop configurations. And that the first along this line was the experiment by Pound and Retzke 59 at Harvard, where they used Mössbauer spectroscopy or the gamma rays of iron atoms to observe this redshift really at the building. I worked there at this building. It was in this Jefferson Tower. Unfortunately, it doesn't exist anymore. So they have erased. That was went through 3 floors in the building, and they removed, unfortunately, the holes where it was done. And now the theoreticians sit there where basically the machines were for the receiver station top, and the basement is now used for other experiments at this building. Good. So what did they do? So that roughly 20 meter separation, they placed the sender and the receiver box there. The sender was a light source of gamma rays, so in particular this Mössbauer Eisen 57 isotope. Mössbauer, because you have almost the recoil is negligible, so a perfect crystal structure, which means there's no uncertainty in there's no noise, so to say, from the recoil uncertainty. So everything goes really into the gamma rays. It's a very precise tool and method to work with to measure frequencies. So if everything is fine, then you have here a receiver. Up there, there's a detector, and due to the redshift, you will observe that the light that's emitted here is redshifted up to this level of 22 meters, which means that there's a mismatch in the absorptions, because you need precisely this energy gap, and if it doesn't fit anymore, then you see there's a few absorbance at the atoms here in the higher level. How could you compensate for that? Well, you basically apply a velocity that introduces a Doppler shift, and it corrects this redshift. And that's the way to measure the redshift that you get, that you see, okay, I have to move that fast to again absorb my atoms in there. And really they were able to with very high precision. A few years later, this kind of redshift in there. The other way to see it is to say, you can also say, well, there's different ways to explain the story, which makes it so interesting. You could also say that the clocks of the atoms itself tick differently. Here at this speed, I would say that the clock is different of these atoms than that atoms, and therefore effectively turns into a redshift in there. That's also directly linked in the formula with the frequency shift. And by that, you can also explain why there's no resonance condition for these atoms there, which effectively have a different clock cycle than this. But the importance for me is that was really the first experiments that did it on the ground with a laboratory framework as something that you can really do in the lab. Based on these ideas of redshift and different clocks at different heights, there was an avalanche of experiments, and I picked out a few that were the milestones in my eyes. So Haffel and Keating in the early 70s put atomic clocks on planes, sent the planes around the Earth. They were flying around here, and they could really, again, with very high accuracy, about the order of 9%, see a difference in the clock of those atomic clocks, different clocks, time dilation of those atomic clocks, and that was also confirming that GR actually is really correctly describing our world. Well, how can you increase the effect? Well, you go to bigger distances from Earth to ground, and then a few years later, people put a maser, that's again an atomic clock, on a rocket and went up to 10,000 kilometers here. And then we saw Levine and others confirmed with higher accuracy, actually, with Gravity Probe 1, this time dilation due to different heights. It goes on for many years. Actually, there's even something happening a few years ago, which is in Japan, but let's pick out this one here from older slides. So nowadays, people get such a high precision on atomic clocks that they can really observe different time dilations when clocks are just separated by less than a meter, in the order of 30 centimeters. People could observe this kind of different time dilations, as well as clocks also corresponding to different speeds of the clock. So even speeds as small as 10 meters per second nowadays can be resolved with the best clocks due to the GR effect. And there was also, I think 2 years ago, people are able to observe this kind of clock differences with more or less regular atomic clocks, so they can almost buy commercially, placing them at the ground of a high tower, at the top of a high tower in Japan. And also could there observe this time dilation. Well, this is the redshift, and the fourth concept I would like to emphasize, because this gets us closer to the experiments we have to do, is the Shapiro Effect, which goes back to Shapiro in the early 60s, who sent radio light from Earth to Venus. That's reflected at the surface, at the atmosphere, and comes back. And you're seeing there's a time delay of 200 microseconds, which can be only explained by having this space-time curvature here due to the Earth and the Sun here in the middle. And that was the beginning of this kind of light bending, so to say, due to masses. There was a continuation of other experiments to improve these results. A few years later, there's this famous high-stack antenna in Westford, where they continued more precise experiments with well, about 10% accuracy. And nowadays, people use satellites, which they place in a good position, so to say, that the light or the radio waves go close to sun, and then you see here with precisions up to 10 to minus 5 results that confirm that are that close to what GR predicts. And that's right now the research this year with the Cassini probe just a few years ago. And I guess Cassini is still flying in the orbit and is still used for investigation. So these are the, as you see, the classical tests that people used, so to say, a classical light or classical physics concepts to probe the effect of GR. Of course, it's interesting to see how quantum physics is interplaying with gravity. And there are a few experiments, and the first is the one I would like to mention. It goes back to neutron interferometry, which was among the first generations that people had access to a single quantum particle. Neutrons are easy to, well, you get them from reactors, but they're slow, so you can easily manipulate them. And there's experiments by Colella, Oberhauser, and Werner, who basically built a Mach 10 interferometry for neutrons. So how does it look like? A neutron comes here, then has the chance to go two paths, either this way to C or this way to B, and then it's recombined here at D, where after this slit, you don't know if this path was taken or the other path was taken. So regular Mach 10 interferometry. point now is that they were able to tilt this, that C and B have different heights. So they could basically flip this, that C is higher from the Earth than B or vice versa. Basically, it's a rotating wheel. And by that, they were able to introduce a phase because the neutrons explore a different phase, in Newtonian phase, with respect to the height. You see, this comes in here. And when you now rotate, what you see is you get a phase shift linked to the rotation of the plate on this plot. And here, that's the fingerprint that they got this phase pattern due to the gravitational influence. Okay, you can also explain it as an Aharonov-Bohm phase because it's affecting here really just as a phase on the involvement here. And that was the beginning in 75. The quantum system can explore the interface with gravity. Good. Let's put things together. What has been done and where do we see our need for our experiment? So I make a table where I say, well, this is the gravity concept. There's Newtonian gravity, so a result can be explained by Newtonian theory, and there's experiments which really require the general relativity with curvature of the metric and curvature of space-time to explain the results. So with classical physics, Newtonian gravity was, explored and confirmed since the 17th century. If we look to the things we just went through, then there were the classical tests of GR, okay, with time, with clocks. So basically, these are for me like classical devices, just things that measure clock, even though they use atoms. It doesn't require actually quantum mechanical principles besides maybe some details, but it's more or less a classical thing for me to a tool that explores general relativity. With quantum mechanics, I always implicitly think of the particular features that quantum mechanics provide, which cannot be found in classical physics. That's the superposition principle, quantum entanglement, and so on. And I really think about those features which are interesting to face with gravity. And that was done, as I showed just before, with neutrons. So they use really single particles, superposition from neutrons, and they've seen this phase. But the phase here, and that's the important point, can be also explained by Newtonian gravity. So it's not really needed, or actually cannot basically explained, or it's needed to have this general relativity concept here because of just having a phase. And that's true also for follow-up experiments based on cold atoms and even Bose-Einstein condensate. All those observe phases due to gravity, and therefore a fingerprint of this Newtonian gravity, but not of true GR effect. So in essence, the problem that we have seen here is that all of the beautiful experiments done so far, okay, do not provide unique signature of GR and quantum mechanics in a single experiment, okay? Because of this reason that those experiments could be explained by Newtonian gravity. So, and that was the birth or the reason for saying, okay, what about of photonic quantum systems, because photons are intrinsically massless, okay? There's no way to use this to explain this by Newtonian gravity. By having massless particles, you automatically link to GR and space-time, and that's the reason why we are dedicated to do experiments with photons and seeing influence there. What's the downside? Well, photons have no mass. That's good and bad. Bad because it means you have a way stronger interactions or effects of GR, which makes the experiment much harder to build and to basically observe the effects from general relativity. But let us get there by seeing how the experiment works. Okay, so in essence, we have to build a photonic interferometer, which can be seen as the Shapiro version in the quantum regime. So let me put the pieces together how we build those things. So of course you want to see the difference of gravity of GR, which is linked to height when you use Earth as reference system, and we work with light. So let's consider the following case: you have a laser, you send laser light to a receiver, and then of course we know there's a particular frequency given by the laser or the atoms and so on. And that's here. You can also link this to a clock that this person has, and he measures the frequency coming from the laser. Well, that's in this reference frame. If you have another reference frame and put the guy here up in a height, let's say a few floors up, then this can do the same. You have a laser that sends a laser light. This guy takes a clock and measures the same frequency if he is basically there in his own reference frame. However, if you be an external observer and you compare those two scenarios, that you have one here at the ground and one here in the upper level, so separated by some distance height, then you would observe the redshift that this upper guy observes due to having either different clock in his hands, or if you would prefer this explanation, by having here this redshifted laser light up there. And that's precisely what we would like to use for our experiment. We have in mind to take, instead of lasers, quantum light, single photons. We take basically two paths. One is here on the ground level, other path here in the higher level. And when you now take a beam splitter where there's a 50% chance that the light is going this up here, this path, so that's a mirror, or this path, okay? And then you recombine, and then you measure the light coming out this detector, that detector. Then you will see that there's a phase shift because this light up here observes this red shift. And you see the wave packages to come out, they're not overlapping anymore. You see that there's different phase shift. And the phase shift is really dependent on the height. So when you get closer, then we see also the phase shift here is smaller, and therefore that's the link to the gravitational influence. And that's the thing you can measure at the end, even though it's a tiny effect, but in principle you can measure. So what do you do in reality? Well, you build something like this that you have now here, beam splitters, mirror beam splitters, and then you will see at the end that you measure different clicks at this detector or that detector. You see here, this detector will go up. We get more clicks when you increase the height, whereas when you go higher. So due to the phase shift, we get more clicks here. And of course, the clicks that you have more here are reduced by the complementarity amount on that detector. That's the essence of the experiment we have in mind to do. Good. Well, the theory of that goes back to actually just a Buchner's group who looked at clocks at different heights and how they interfere. This was then turned into something we can do. So we turned this into our clocks as photons and redshift. And we did investigation with a few experts. We are super happy about having this collaboration, in particular Piotr and Nergis Marvalvala from the MIT LIGO group, so LIGO at MIT, who helped us to make a proper calculation and investigation, at least from the theory. Does it work? Can we do it? And do the numbers fit together that this is worth to do an experiment? And the short answer is yes. And I can show you now what is the result. So the thing that we have in mind is, again, this interferometer. And the question is, what actually the parameters that we need to observe a phase shift? Okay, and the phase shift here is given in essence by the length, okay, of the interferometer times the height. In other words, the area counts for making the phase shift possible. So you see that's good. They have length and height here up there, but the problem is it's divided by c cubed. So in essence, the phase shift is tiny. Okay, that makes a challenge. So we need a big interferometer, and big is always hard because big requires it's hard in terms of stability and also in photon loss, because single photons are hard to get in a controlled manner, and you would like to keep them. You want to have them as long as possible here. Traveling, and then you can observe many of those at the detectors. Good, so that's the phase shift, which is linked to height and length. If I put the numbers here in more quantitatively, we also have beautiful work with follow-up paper here with Piotr's group and Beck about properties of light in the fiber, because it comes up in a second. We have to use fibers for achieving these long distances. And why? Well, before I come there, let's see the numbers. So it turns out that the gravitational interaction changes the wave vector by this small number, 10 to the minus 9 per 1 meter height. Okay, let's say if you just go 1 meter in height, which is a thing we can do in the lab, that's say a height difference if we're comfortable to stabilize things, then we have now to increase the length. And if you put this number here, 100 kilometers, which is the longest length we can do with optical fibers. If you go more than that to bigger lengths, then the losses are so big that at the end no light comes out. So if you take 100-kilometer fibers here and there, then it turns out that the phase shift you will observe due to gravity is 10 to the minus 4 radians. Okay, well, that's small. Okay, but it's not crazy. That's something that people normally can read out. If they have strong lasers and these phase shifts, they can read with no problem. The thing that's new here is, well, you have to stabilize a very big interferometer. So in essence, you have basically a sensitivity of the difference in length, okay, is 10 to minus 16 over this entire interferometer, okay? It's called strain sensitivity. So just to put this in respect, LIGO is 10 to minus 21 or 10 to minus 20, okay? So we are not LIGO, of course, but we are not that far away what big LIGO achieves, okay? So in our eyes, that's really the maximum you can probably achieve in the laboratory as a tabletop experiment, and having this kind of tiny difference in length you would like to read out over this beast is of course challenging in terms of stability. I'll come to that in a second. Good, and as I said, we cannot have more than 100 kilometer fibers because here the transmission is already just 1% per single photon. So here the numbers summarize that's the phase shift for this formula. We have this hydrophometer, the length of 100 kilometers, and we expect this time minus 4 radians phase shift. However, for reading out such a phase shift, you want to be, that's the rule of thumb, 1 order of magnitude more precise. So we need actually this resolution, which corresponds to being able to see a tiny frequency shift of 10 to minus 17, so delta F over F in this regime, which is very hard for lasers. We come to it in a second. So the take-home message is, it's not easy, but we still think it's possible and worth to do. So that's a schematic drawing of our setup. So we come to that in a second and later. We have actually not one arm, but two, so three arms, not 2 arms, but 3 arms, because we have to reference different heights, and we had in mind how we can basically get some kind of tuning in there, because you would like to read the signal not as a constant factor, but something that you can tune to be sure, yes, that's your signal, not a noise contribution. And on the right side here, you see all the things that we investigated, what kind of noise comes up. There's fiber noise, there's systematic errors, there's even seismic noise, acoustic noise, and all those things were investigated. We learned a lot. So I must admit, I was underestimated by orders of magnitude the complexity of this experiment. And therefore, I'm so proud that we have this excellent team in Vienna that really digged in, figured out what can be done, many trips to MIT guys to help us in reading out noisy signal, because they're really the world experts in telling you, if you know your noise, then you can handle it, and then you can read out the signal, and we know now which frequencies we have to use. We know now what kind of decoupling is needed, and also with the help of Piotr, we could prove that there's no fundamental issue coming up from Sennak Effect and Earth rotations that spoil us too much. So we know those now, so now we can really design the experiment to separate the noise from the signal. And you see that many things that have to be considered. I leave it here because I rather focus on the scientific vision that we have when of the experiment. Good. So if I have to summarize, the experiment would not be possible without those world experts we are so privileged to work with. As I mentioned, Nergis Group and MIT, PTB, I will come to that in a second, is responsible for giving us the world's best laser signal. Best in the sense, the smallest noise, okay, the highest frequency resolution. This is something which really makes our story so nice here in Vienna. And without Piotr, we would be basically certainly lost in understanding GR and all the effects that would come there. And we're very, very happy that Piotr is guiding us and working with us for already a couple of years in this interesting journey. So what do we have? So how does the experiment look like? So we have now, see, that's not 2 arms, we have 3 arms. As I mentioned, we would like to switch between different heights so we get the modulation of the signal, because here's a stronger redshift than there, and then we can really read out that. So we learned this from MIT. If you have noise, you have to modulate your signal that basically that you can read out the frequency of the signal all of a noise floor. That's one thing. And to stabilize our this 10 to minus 16 strain the arms, we take now the best lasers we can have. So we have the best lasers commercially viable in Vienna, and we can boost it by a factor of 100 if we connect it to a laser coming from PTB in Germany. So that's so PTB is the Berlin, Braunschweig, it's the NIST of Germany, okay? Metrologieanstalt, Deutsche Metrologieanstalt, who has the atomic clocks as reference in Germany. And they have atomic clocks which are cooled and cryogenic, they're more precise, and we can get such a signal to make our laser better. Why? Because you have to stabilize these arms very precisely by having additional interferometers, and they're not shown, for each arm to basically compensate every fluctuation that they're stable and can read just the GR signal in our setup. So that's the schematic drawing. So we built something here on a very stable platform designed by MIT. Here the fiber coils at different heights, which you can switch between those. Each fiber coil actually has its own virtual clock. Okay, so we have very precise lasers stabilizing these arms. Here's our laser here, and actually that's an interesting side story. So this experiment probably supports the clock dissemination in Europe, because PTB has clocks in Braunschweig, that's by Hanover. They have fibers in Germany to send this across, even to France, to compare clocks, you know, for geodesics and other interesting experiments. And there's currently a fiber going to Munich. And we got money. So Piotr didn't mention, we got money from different sources now for getting the extension from Munich to Vienna, that we can connect ourselves to a laser signal coming from Hanover. And with that, we can synchronize our lasers here in the way that the resolution is boosted by a factor of 100. Okay, we're not sure we need it. Best case, we don't need it. Worst case, we need it. But if we need it, we have access to. And now our experiment somehow helps that PTB sends signals to Vienna. And now, as the rumors were spread around that this is happening, other groups came to us and said, hey, we would also like to have this access, because we work also with atom clocks, TU Wien and so on. And now we shaped a little bit the clock dissemination in Austria, which is a nice side effect. Good, that's the schematic of the experiment. Back to our expertise. So the thing works with quantum light. So that's really our signatures for 10 years. And just make it briefly, what's our bread and butter in the quantum group. Well, we normally take nonlinear crystals where lasers shine on these nonlinear crystals, where there's a high harmonics, a second order effect, which turns into that the blue laser light is turned into two red. So one blue laser photon becomes two red photons. And if you do it in a smart way, you can really generate a polarization entangled state. That's something we generate here. Nowadays, it's more trendy to have actually artificial atoms. So the problem here is it's probabilistic. You never know when a photon is coming. So people thought, is there a better way to get a system where you push a button, always a photon comes out? And that's not yet possible, but in principle, it could be done by these artificial atoms where you build so-called quantum dots. You build semiconductor structures. You confine it in 3D that they behave like as a single atom. When you shine laser there, then basically you excite and you get a photon out, and it comes out coupled in a cavity. So it's efficient. And we have these quantum dot sources, which are way brighter, let's say order of magnitude brighter than these sources. And we have in mind to use also those for the experiment, because we need every photon for statistical reasons. What's the challenge? Well, that's a technical detail, but the best wavelength for fibers, and best wavelength means where the losses are minimal, is the so-called telecommunication wavelength that's nowadays used everywhere for whatever, phone calls and so on. But it's at this wavelength, it's 1.5 nanometers. And that's an unlucky wavelength, because detectors are not very efficient there that we use in regular life. So regular detectors are based on silicon or silicon photonics, and they're very inefficient, just a few %. That's fine for telecommunication business, because they have so bright lasers, they don't care to throw away 90% of the detectors. But for us single photon guys, that was a killer reason for many years to work at this wavelength. But the problem was solved by superconducting technology, which is now on the market for 10 years. And we work with that and even update or upgrade those systems for our needs. And by using so the superconducting material, you have almost 95% efficiency. How does it work? Very simple. You cool down a superconductor to be superconducting. Then you measure the resistance, which is 0 because it's a superconductor. When a photon comes, so you basically have here the superconducting wire. It's here. When a photon comes, it makes a hotspot. Okay, it gets absorbed. And the hotspot means that the flux basically is squeezed to the side. It cannot go through the hotspot here. And if you increase the flux, at some point superconductivity breaks down. Okay, that's happening here. And if this breaks down, then you see suddenly resistance. So, and then when you see the resistance, you know photon was measured there. And you keep the material very small, so it's nanomaterials, for the reason that if it's small, it's cooled down again rapidly. So after a few nanoseconds, the heat is gone, and you see it becomes again superconducting and reaches again this point where it's ready to see the next photon. And that's what we operate. What does it need? Well, it needs a cryostat of the order of 1 Kelvin. So you see here an open cryostat, fibers come in, It would go down many levels to this 1K, 1 Kelvin region, where inside the detectors are sitting. Let's see the detector inside. Okay, the fiber comes, we read out our signal here with these detectors. And now, as you see, well, these are technical details. You can even resolve if 1 or 2 photons are coming, because at the area where the fiber comes, okay, you can put now several detectors that are like put together like these meanders, okay. And this means when 2 photons come, there's a chance that 2 different detectors will see it. 1 photon goes, for example, to the green detector, another photon to the red detector, and then we get 2 different clicks. We can tell you, yes, 2 photons arrived here. And for this 4-element systems that we have, the overall efficiency is, you see, 22% is for each detector, this times 4. So really in the good 90% regime for our detectors at this wavelength for our system. The message is here, we are happy and glad that we have the technology and capabilities to work efficient with photons as it's required for this experiment. So I talked about single photon and how gravity is influencing our quantum light, but of course, we want to have a real signature of a quantum feature, because single photon superposition is at the end the same that would you observe by laser light in there. So it requires more arguments why the single photon is different, why the single photon detection you have to treat differently as a regular laser light, even though I think it is different, but it's of course nicer to have a stronger signature of quantum mechanics. And what could be better than to use entanglement or really entangled photon pairs? So how do we get there? Well, we can do it, and we use a particular feature of light, which is again something that we use at the daily business. And it's really linked to the bosonic nature of light. How come? So if you have now a beam splitter where you have 50% chance that light, say 1 photon comes here, that light is transmitted, or 50% chance to be light is reflected, then the following happens if you have now 1 photon from this side and 1 photon from that side. So when they come and these wave packages overlap, so you have to describe them by quantum mechanics, then these photons interfere, and the interference leads to the fact that both terms are transmitted, that this one, and the terms are both reflected, okay, that would correspond to that term. So transmission, reflection, turns into 0, okay? They, by interference, are gone. And there's a few ways to explain this, but if you be a quantum optics person or quantum mechanics guy, you would say, well, that's the bosonic nature. Photons like to bunch, they're bosons. There's nowhere to be separated, and they go only as 2 photons there and 2 photons there. One way to explain. Other way to explain is, if you're an optics guy, you would say, well, we know from each reflection here, you get an imaginary I phase shift. And also from this side. So each photon gets an I phase shift if it's reflected. So you see reflection 1, reflection 2 gives you each time this I times I squared is -1. So you would understand from optics also, well, this term must cancel because of this reflection part here. And that's the case. How do we observe it? How do we measure? So what we do is we look at the coincidences. That means we look at the case where a photon comes out here and there. We look at these clicks from both detectors simultaneously. And that's drawn on this axis, coincidence measurements. And now we tune the delay of a single photon here. So if the photons arrive at different times, then there's no interference. And you will see, at this case, let's say here, there's the big difference in delay. You will see coincidences because there's no interference, and photons can go as they wish. But as soon as you change the delay that the photons start to overlap, then you see, so you change the delay that's here on this axis, then you see that at some point, as soon as the photon starts to overlap, the counts go down. So the coincidences vanishes. And the best point is here, when there's a perfect overlap of photons, then you see there's no coincidence measured because all photons interfere in such a way that they bunch into this state of 2 photons left or 2 photons right in a coherent or in an entangled state. Okay, and that's basically what we do. We tune our delays of light of single photons, that we always observe such a missing coincidence, which is the signature, yes, photons interfere there and can work with it. Good. Why do I bring this up? Why do I teach you about photons bunching at the beam splitter? Well, that's our entangled state. And even better than that, it allows also an increased sensitivity. How come? So if you look at the beam splitter and the photons interfere, that 2 go up here and 2 go up there, then you have an entangled state. So they are really in this non-factorizable state where 2 photons and superposition of, let's say, if n is equal to 2, that's the state, 2 photons up and nothing down, or vice versa. So this corresponds to a path entangled state, okay? And the nice feature why this is interesting for many years in optics is that it increases sensitivity as well. So what do I mean by that? So imagine you have this Mach 10 and you shift now this little beam splitter. So with homeschooling, let's take it. So when you're not, say, forget about gravity. Let's say gravity is gone, and for a second we just tune this, shift this mirror. Then you change the path length of this arm. And in essence, what you do is you will see at the end that you have interference because we're changing this path length. But now when you write down the state in this entangled way, that basically the photon number entanglement, let's say one photon up and down or superposition of n photons or 3 photons, then you will see that the oscillations here increase with the number of photons, okay? Because each photon contributes to a phase here. Each photon carries a phase. So if there's one photon, it's EI phi, 2 photons, E2 phi, and so on. And that's basically the way to increase sensitivity, because now you need to move not that far to get already like a λ/2 resolution. So let me show you a picture to that to explain what I mean with that. If you just send one photon, which goes in superposition, then you'll observe if the lambda wavelength of this photon state the interference pattern. And you know, for resolving a distance of light, you have to go from top to bottom. You need λ/2 as the resolution. It's basically the limit that you have. There's other limit and others, but in principle, that's the rule of thumb. Well, if you have now access to an entangled 2-photon state in this kind of manner, you gain this factor of 2 in phase, and you see the oscillations are twice as fast. That means you just need to go half the way to get top to bottom resolution, and therefore you have enhancement effect of 2 in the resolution and so on. So actually what you have here is a light that allows to go to the Heisenberg limit of resolution, which is nice. So what do I want to tell here? Well, if you have quantum entanglement, you benefit by having better resolutions, and that's the thing you can use also for as a signature for our gravity experiment. And this is called this kind of classes of light where you make this path entanglement. It's called noon states because you write it like N00N, and people develop this kind of catchy name for this kind of experiment. Good, and that's precisely what we have in mind to do. So we basically have in mind to send also 2 photons. We put them in perfect overlap, and then we hopefully see this enhanced resolution at the end, which is a signature for our experiment that we have also quantum light being affected by gravity. Good. As a run out of time, I would like to show our current status of research. As I brought it up, it's very hard to build such an experiment, and it makes sense, of course, to start with a little lower level of sensitivity as the first preliminary research. So where are we right now? So thanks to Piotr and his team and Thomas, it was shown that the Earth rotation actually introduces a Sennak effect. Okay, I come to that in a second, but it is. And it's bigger. It's big, quite bigger than the gravity. Okay, that's bad. But the good thing is, Sennak effect is a geometric story. So by playing with geometry of the arrangement of your setup with respect to the Earth axis, okay, you can either make it stronger or weaker, or even put it almost to 0. So in principle, we know how to handle the Earth rotation if we can place our setup in a good angle. But being aware that this effect exists and having in mind we anyways want to work with the Earth and the mass, why don't we use this for the first experiment? And indeed, we want to use the Earth rotation for testing our sensitivity, and that takes us to the thing that's right now built up in our lab. So Earth rotation is based on a Sennak interferometry, which is in the field of this optical gyroscope. Okay, so rotation or observation of rotation, which is an active field by many groups for seeing tiny fluctuations of the Earth rotation due to tidal effects and so on. But how does it work? So I give you hopefully a brief introduction that's not too still allowing you to grasp the basic idea. So the Sennak effect says when you send light, okay, here it's a beam splitter, you send half of the light this way, there's the red arrows, and other half of the light, the blue arrows this way, okay. Then you can adjust the path that they interfere, and all the light, for example, comes out, let's say here at this detector. Now when you start rotating this light, then you effectively change the wavelength of with the rotation and counterclockwise of the rotation of light. Okay, and by that, by rotating the arm, you see a different phase shift, and you can observe a different intensity with respect to the rotations here. That's called this passive sensing that you hear introduced by this rotation. Nowadays, people do something more complicated because it's at the end more sensitive than just looking at detection here. They put non-linear materials using a lasing, the laser systems in there, which observe these rotations by changing the laser light coming out there, and they look at detectors also at the end, which are influenced by detection here of these basically active materials in there. What's impressive about those things? Well, this is called this ring laser gyroscope, where they send laser light clockwise and counterclockwise with respect to the rotation, and they're super sensitive. So it's impressive just to mention this. They build lasers, this kind of ring lasers of big sizes. So the area counts. The bigger the area, the bigger the Sennak influence. So the small ones have 1 square meters, but the bigger ones have almost 1,000 square meters. Okay, with big perimeters. And what last thing that you see is they are able to observe deviations of 10 to minus 7 up to 10 to minus 8 with respect to the Earth rotation. So this omega is the Earth rotation, and they see these tiny deviations of the Earth rotation. And this allows to observe tidal effects, and hopefully in the future, that's what people claim, even frame dragging or this land steering effect. Okay, that's don't want to go into that because I would like to learn more by myself how they do it. But it's amazing that this kind of sensitivity can be achieved with such lasers and so on. But it's not really what I want to do. I want to just prepare the stage for our experiment, which is we go to fibers because we have to work with fibers anyways. Fibers are neat because they have a quite good stability over long terms to measure here our Earth rotation with a fiber gyroscope. How do we do it? And now I just show pictures without equations. We do the following. We take a laser source. We send 2 photons here. They come over here. And then what we do is there's like that's basically so these photons are in this particular orthogonal polarization state, horizontally and vertically polarized. If you want spin up, spin down, there's a Stern-Gerlach explanation. And we project them in a different basis. So we rotate them in terms of optics, which allows to get this kind of state. 2 photons must be either H or 2 photons either V polarized. And this gives us also a path entangled state if we have a splitter that splits the polarization. Okay, so if the H and it does it. So it means that the H polarized light goes this arm and the V polarized light goes that arm. Okay, and they go through these coils. There's one coil of 1 kilometer, second coil of fibers with 1 kilometer, and they go through this big 2 kilometer loop. So the H component this way and the V component the other way. Technical details we also correct for birefringence. We take the fiber course at particular angles. These are just details that we are important for optics that it works. So the point now is, according to the Earth rotation, if you place it properly, so basically you see the maximum effect of the Earth rotation, that's 47 degrees. Then you will see a tiny phase shift here due to the Sennak effect. And since you have a 2 photon state, it's even enhanced by this factor of 2 here. Okay, so Sennak effect is the phase and enhanced by factor of 2 because of this path entangling photon state. And when the light comes back, then we catch it here and we project it to those different terms. This is details about optics. But the point is the amplitudes of this term, or this polarization term, or this polarization term, you see both H, both V, or orthogonally polarized, is basically is linked, okay, to the phase that we catch here. Okay, so by looking at the end, what's the amplitude of this term, or this or that term, gives us the signature about the phase we got from the Sennak effect. And that's what we do at the end. We split the light, and we measure HV component, we measure both photons here, 2 H components, this one, or we measure here at the end 2 V components according to, well, to basically this kind of phase that we get up from the Sennak. And what do we get at the end? So this is just the cosmetics. What we get, we expect for our Earth rotation a 3 milliradian phase shift, which turns into a slight imbalance of those terms, which is seen as 25.15% probability to get these 2 terms and 49.7% of this term, which is different to having perfect zero phase, if there's no Sennak effect, but this is equally balanced, this is 50% and this is 50%. So we see this deviation as our basically as our signature. So as I mentioned before, we would like to see signal by having something tunable, okay? Because a constant signal is always a pain, because they were never sure if this is statistical error or constant error. So how can we tune it? How can we switch on and off the Sennak effect, so to say? And we do it by placing here an optical switch. That's the reason we have two coils, and the switch basically makes this. It twists the connection of fibers in a nutshell. That means in one configuration, they are opposite polarized. That means the light goes, so it goes like one direction and then the other direction here, the light. So the Sennak effect is compensated because half the way it is left spinning and the other half the way it is right spinning the light. So it goes back to zero. Or we change the switch that they add. So it's left spinning and again left spinning. Okay. So by that you have two coils which are like either like this or like this connected. And that's the idea of our very good optical switch here. And by that we can switch to no Sennak effect to Sennak effect. And this allows us to observe those things. And that's happening in the lab. So how does it look like? That's the lab. It's here. These are the two coils. So we here see it better on this side. This is the one coil. This is the other coil with 1 kilometer length. The switch is not shown here. It's actually at the end. It's a small thing in the frame, and it's oriented in a, how to say in English, cadencia, of the gimbal mount, where you can change the angles of the entire Sennak interferometer in such a way that you have the biggest effect with respect to the Earth rotation. But as you know, the Earth is rotating, and we have our latitude is 47th degree, so you have to of course correct by that to have the maximum Sennak effect. And that's the reason we have this arrangement here for our setup. And that's the first step of doing a precise measurement, which is soon followed by a big interferometer for observing gravitational effects in single photons. Good. With that, I hope I could shine your light into our plans and vision. In essence, the summary is here. So we have now a precise interferometer where for the first time, okay, quantum light will be used to observe the Earth rotation. So we started continuous laser light. That's nothing special, but it's more like alignment purposes. And soon we want to switch to these two photon noon states, as shown before, to really use quantum mechanical enhancement. And it's called quantum enhanced sensitivity or quantum metrology in our community, to see the Earth rotation by noon states. And based on the insights here, it will be the next generation of interferometer, which is really has the plan to see the gravitational effects on quantum light, on single and entangled photons. And we believe it's important to do so, this experiment, because the fact that if these massless systems, okay, really massless particles, means that there's no way to explain our results by Newtonian gravity, and therefore we really go beyond Newtonian descriptions. And it says, well, it's really a unique fingerprint that we have a GR effect measured on quantum light, and that's the vision of this. Good. With that, I want to thank so much the team that really is from day one, and it's already a couple of years, 5-6 years ago, supporting this research project. There's Christopher Hilweg, Bob Peters, and Raffaele Silvestri working on the experimental side and in my group. But we're very privileged and happy to have Piotr and Thomas. I couldn't find a picture of Thomas. I tried to steal one on the internet, but I couldn't find the proper one. So it seems it's really an eyewitness program that Thomas is currently protected. I want to thank Thomas and Piotr so much for being open to support our, at that time, crazy idea, maybe, this research direction. And without the help of Piotr and Thomas, we wouldn't be there yet with all this insights, understanding, and they never get tired when we ask simple questions in their eyes about gravity, and they are so helpful for us to make this experiment happening. And I'm really happy for our collaboration, which happens with tourists, but we wouldn't be there without the serious support of our friends. Good. With that, I thank you for your attention, and I stop here, and it seems still have some minutes left for questions.
Okay, thank you very much, Philip, for this excellent, clear talk and interesting talk. The floor is open for questions. I try to see who wants to raise his hand. So before you think about the question, let me ask you a question.
Kann ich kurz einen Kommentar? Ich glaube, ich habe meine Hand gehoben.
Yeah, now I see it. Yeah, okay, Herbert, go ahead.
Only a short commentary. You were talking about the cow experiment. Yes. And since I'm from the Technical University, I want to bring in the name of Helmut Rauch, yes. Who was, so to say, involved in these neutron interferometry experiments, mostly with this 720 degrees rotation. And you pointed out that the cow experiment is actually explained in Newtonian gravity. And Helmut, in his, unfortunately, he's passed away last year. And so, I mean, in his late book, he has also an explanation using, so to say, Eigenzeit description within the Schwarzschild geometry. So in that sense, it has a little bit of flavor of general relativity. This was just a comment for the first experiment you were talking about in the quantum regime.
Yes. So notice comment from Helmut Rauch. Thank you for pointing this out. Of course, neutron interferometry would not be there without Helmut Rauch. He was really a certain pioneer. You know, he influenced people.
Yeah, we are very sad that he passed away, but
absolutely, yeah,
certainly very influential.
Yes, of course. But to come back to light, with light, it's clear that there's really no mass, and you can avoid any additional arguments that Newtonian gravity plays a game there. So that was for us the vision to do something with.
No, it's more or less, I mean, the equivalence principle that you would expect. I mean, if you do it either in curved space-time or you do it in Newtonian gravity with acceleration. So if this fits together, then it's fine, but should be corrections.
So
I have a question.
Go ahead.
May I ask a question?
Yes.
Okay. So the question is related to the middle of your talk, where you have shown us a laser beam, let's say upper and lower. Yes, there were two laser beams, and you measured something, which the phase shift, which depends on the difference of the levels of those two beams. Yes, but and this was redshift, let's say. And my question is very general. Can you inverse the experiment? Can you pass from red to blue shift, or inverse in time, or whatever? So that the phase shift will be opposite, and then you come on the same let's say experiment, but roughly the laser is up and the detector is down.
Okay.
You understand my question?
Let me rephrase it if I understand. So you're saying, can we have the opposite, that we get the blue shift by putting detectors down, and you? But
yeah, I can say that the length which is in this phase shift is negative. You know, this H becomes not positive but negative.
It boils down to rotating the machine.
Yes, but isn't it the same? Because you can, as soon as you have a difference in height, you can basically, depend on where you're standing, you can talk about red or blue shifts. No, I think so. The answer is yes, but at the end, the bottom line is we want to see a red shift that can be only explained by GR. No, so and I think the answer is yes. So for me, what you were saying is, it's really a question about your reference system, where you put yourself. Do you put on the lower level and you see if something blue shifted, or start from the ground, something red shifted? So the answer is yes. But it's
but
equivalent.
Can you do the experiment parallelly? You know, just two different experiments in some sense. Then this, can you see some symmetry with this delta phi?
So in some essence we will do that. Okay, so because we build it, we have three levels. There's one height, height 1, height 2, height 3. Okay, so in that essence we will play with different heights and switches, because we need a modulation. We need a signal that says a stronger gravity. We need different gravity influences, or different redshifts that we can read out at the end as an oscillation, because that's our signal. So we have to play with this concept, because we learned from experts, that was LIGO, that a constant signal is always hard to read out. If the signal is always there, then it's very hard to separate from everything else. You need a modulation. And this probably brings it back to your suggestions. Yes, we have different heights. Okay, let's say small red, big red shift, or if you put yourself in the middle, one is red, other one is blue shifted. We have this, and we see the modulation between those. And that's precisely what we build with the help of LIGO, because it's not simple at all to build a device so we can modulate that. And this, I think, brings it back to what you suggest. We see both influences, or the different relative different influences of gravity. So the answer is yes.
Yeah, thanks.
Okay, further comment? If not, I may ask a question concerning systematic errors. How important is it that the velocity of light in that fiber is constant, or is equal? I should say equal, or this is.
So thanks to Piotr, I was taking a closer look on the propagation of light in fibers. So thanks to Thomas. Okay, so your question about the speed of light, as long as it's constant, okay, and nothing is changing over time, it's fine. So at the end, we have one fiber up, one fiber down, and then there can be even a different length or so, or there can be even different in some aspects. As long as it doesn't change over time, it doesn't matter. So you build your device, then you tune it that you see the interference as you expect, and then comes the challenge. You switch on magically the switch who says don't move, okay? And don't move means from now on they have to consider all the noises that might come up. There is so a nice story I like to tell. When people investigated about fibers from the practical aspect, we said, look, who are the fiber experts to ask? Okay, we went to LIGO. They will let LIGO work with Revise. Said in the beginning he worked with fibers, but he's not too sure about all the properties and so on. And after asking 3 people, were pointed to the US Navy. There's a Navy Research Center, and they're the world experts in fiber. We went to Washington, D.C., and we learned there's a small fraction they can tell us, which is even amazingly knowledge, and a big fraction they cannot tell us. Why? Because fibers are used at submarines for being surrounded, the submarine fibers. And if there's a sound wave, something like this coming, they give a phase shift from the fiber, and they can read out precisely which direction even the sound wave from another propeller comes, okay? So I like this story to tell that actually the Navy was super helpful in us for building this interferometer. But back to your question, as long as we know as long as it's stable and we know what's happening in the fiber, there's no problem with the speed of light. Okay.
Thank you.
Okay.
Is there any further?
Yeah, so I have a question.
Yes.
Yeah, so we've been interested in various things related to polarization, and we're trying to do some toy calculations concerning propagation of polarization, essentially around an optical fiber in a gravitational field. And so I'm curious if what's your expectation? Is it conceivable to have a stable sort of actually experimental setup of the type you're considering, where you would be able to observe effects related to polarization of the light?
Very good question. The polarization is a big issue. Okay. So in our dream world, we would like to keep polarization fixed. We don't need to consider that. Okay. One way to do it, you would take polarization maintaining fibers, which are built, as you know, that it doesn't work because they're too lossy. Besides being too expensive, it would be millions that we have to spend. So we have to work with regular fibers. The polarization is rotated. Okay. So we learned also here from LIGO and the Navy guys that you can stabilize fibers as long as ours in such a way that the polarization is of course changing, but it comes with a given input state. Polarization comes in and the polarization comes out a certain degree. We can keep it stable in such a way that there's that basically this will not affect us too much. So we can freeze everything to a degree that the polarization is not drifting in the fiber. Okay, and that's the challenge that we that's what investigated for last year in stabilization techniques, that the polarization drift is basically non-existing or very small in the fiber. So we learned how to do that actually.
Oh, that's very interesting, because I mean potentially there is a sort of geometric optics effect on the polarization vector in a gravitational field.
Yes. So you're saying so this I would like to pass on to Piotr, because they did calculations on polarization, and I think, if I remember correctly, it shouldn't affect in the fiber. So you're saying, is gravity affecting polarization in the fiber? This is what you're saying?
Yeah, because I mean, there are similar calculations have been done for massive spinning particles, and
yes.
I think, but I mean, this has not been done to the end. I mean, we should discuss this with Piotr eventually, that you can have a similar effect on photons in a fiber sitting in the gravitational field, but this needs to be investigated. I mean, this has not been, we have not finished this, but I'm it would be curious if one could potentially see also such effects on the polarization of photons.
Can you hear me? Because I had problems with the microphone.
Yeah, yes.
Yes.
Would
So,
you like to comment? Yes.
Yeah, so just a quick comment. In the paper we wrote with Bobby and Christopher and Philip, we work out the electric and magnetic field after it went through the fiber. So we have a formula for that. My memory is that our preliminary thinking about it, that we will not be able to measure that, but maybe it's a good point in time to just take this formula we worked out and to revisit them. That's one comment. And the second comment is, well, a question to Philip. So how far are you now with the rotation experiment? Do you have numbers now? Is this still in a debugging phase? Or?
No. So the measure right now with laser light. So the numbers are boring to show because this is just like characterizations about. So
no, but I mean experimental results, right? So
yes, we have experimental. So we have experimental curves, which I did not show you, because it takes 1 more month to have something useful. So right now we measure with continuous laser light, and they optimize in coupling and so on. But the plan is that by end of March, everything is measured with single and with quantum light. So the source is prepared, it's ready to shoot, and we have an internal bet in the group that by end of March, okay, so after spring break, everything is measured. So I hope that it looks good. So I would say in a couple of weeks we have the data.
Great. So I'm looking forward to meeting you and
yes, absolutely, should catch up. Yeah, sure.
Thank you. Just to finish, I want to bring up a question we have discussed with you, Philip, namely the question, what is really tested? Is it I mean, is it what has been mentioned, the so-called equivalence principle? Now, the equivalence principle is also valid in Newtonian theory, and it's valid in any metric theory of gravity. So you emphasized several times that this goes beyond Newton's theory. And I think we had a debate on this, and I'm not sure, because after all, one knows that light is, even Einstein, before he put forward his theory, knew that light is influenced by gravity.
Yes,
so,
but here I'm happy to answer in the words that I learned from Piotr, that if you use just the equivalence principle, you offer a factor of 2. Okay, so you have to consider also the change in the metric, so you don't get the right number. Okay, so the thing that we test here is we would like to explain. Our experiment allows to exclude, as Piotr pointed out, some post-Newtonian concepts. If you just use the equivalence principle, then you would be wrong by factor of 2. And here we think it's a true signature of our experiment that you must use GR and quantum mechanics, in particular for the 2 photon states, to explain the results. So the purpose is you want to have one experiment where you need both theories truly, GR and quantum mechanics, to explain the results. And we'd like to see if there's any surprising deviation or not, what you expect. That's the thing we'd like to do here. Oops, I see just right now somebody mentioned I should read a comment. Sorry.
I think it's still a local experiment, but let's leave the discussion at this point because we have to go on. So okay. Thank you very much.
Thanks. I just see there's a comment from Charles Robson who asked me why is the calculus not probing general relativity? the answer is the effect that you see could be explained by just Newtonian potential, okay? So you could explain this without any space-time curvature, and that's the reason we say the cow is, but we just have talked before, but has some limitation in the strength about concluding this GR effect, and therefore we would like to do something without masses where intrinsically there is no Newtonian potential.
Okay, so thank you very much,
Okay.
Philip.
Thanks for the invitation. I'm very happy that I could talk here.
Good.
I have to get out for a second because my kids are screaming for homeschooling, so I'm running back to save some homework problems. Okay.
Thank you very much. Thank you.
Thank you.
Yeah.
Bye.
These are usually the difficult ones.
Absolutely. Okay.
But I turn over to you. Yeah, you're the chairman for the next
I
3
guess
seconds.
so.
Herbert, may I suggest a 5 minutes break for everyone
Yeah,
before we continue?
So shall we meet at 20 minutes past 11?
Very good.
That's
Hello? Can you hear me?
Yeah.
Will some of you be occasionally in this lunchroom where one can say hello?
In this lunchroom, actually, I have been before, but unfortunately, not really.
I mean,
I have tried it, and it looks a little bit like a computer game. So you can move around your little figure, and yeah, when I was in there, there was nobody else.
Okay.
Okay, almost.
Hi.
Hi, we can hear you.
Okay, very good.
I've granted you the rights so that you should be able to share the screen. You're her co-host for this reason.
Okay, great. Let me just try.
Yes, you can start and you don't have to start to talk immediately. Perfect.
So that should work, right?
Yeah, maybe you could make it full screen slow.
Right. That's full screen. And then I can make this small such that, I mean, you don't
exactly perfect.
See the other people.
So, wir haben noch ein bisschen Zeit.
Ja, also vom Screensharing sollte glaube ich, alles.
Aufgezeichnet. Also ich kann alles sehen und ich kann sie auch perfekt hören.
Wunderbar.
Gut. Der Herr Mieling ist so nett und kümmert sich um die technischen Belange. Ich bin da sozusagen nur jetzt der Überbau, der ein bisschen...
Genau. Ich kümmere mich um die Berechtigungen, dass jeder, der Fragen stellen kann, das auch tun kann.
Perfekt. Das heißt, in der Question-Answer-Session kann ich dann ganz einfach, also in den Participants kann ich dann Raised Hands sehen.
Genau, ich werde die Leute, die die Hand heben, einfach...
Okay, ich würde dafür plädieren, das machen wir sozusagen am Ende.
Genau.
Gut, naja. Wir sind schon fast.
Seht ihr eigentlich auch den Balken unten oder sehe den nur ich?
Ich sehe einen Balken. Ich habe meinen Balken drinnen, aber der verschwindet wieder.
Ah ja, okay. Ja.
Der wird von Zoom eingeblendet, aber der wird nicht beim Screensharing übertragen. Also wir sehen.
Ah, okay, wunderbar, weil ich sehe den Balken, aber okay, ja. Dann.
Ja, das ist immer so, wenn man Bildschirm freigibt.
Okay.
Eine Möglichkeit, ja, auszublenden, aber wenn nicht allzu sehr stört, ist, glaube ich, einfacher so.
Ja, nein, also für mich ist das, ja.
Übrigens, ich glaube, ich weiß, was der Piotr gemeint hat. Wenn man auf View Options geht, dann steht da Annotate.